Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and I'm here to help you get ready for the AP Chemistry exam in May. Today we're working on free response question number 6 from the 2019 exam. It was a short free response question, and it was scored out of 4 points, like all short free response questions on the AP Chemistry exam. I always recommend working through the entire problem on your own before you listen to my solution. Whether that means you go through all the parts and then finish the webcast, or you do one part and listen to my explanation and so on, that's fine. What matters is that you try to do it on your own first. Get your calculator, your periodic table, your formula sheet, and get to work, and then finish the rest of the problem. And then keep track of your score as you listen to my explanation. Did you write enough information to really demonstrate your knowledge and to earn all the points that you could? And that's really what we're trying to do. So let's jump right into the problem. Nitrogen dioxide is produced as a byproduct of combustion of fossil fuels. Okay, at elevated temperatures, nitrogen dioxide decomposes according to the equation below. And here's the equation. 2 nitrogen dioxide molecules decompose to form 2 nitrogen monoxide molecules and oxygen gas. The concentration of a sample of nitrogen dioxide gas is monitored as it decomposes, and this concentration is recorded on the graph. That's shown right here. And then 2 more graphs are provided to us, all right, that were developed from the original data. So we've got all kinds of information going on here. We've got a reaction, we've got concentration versus time data. Let's jump into the actual question itself. Part A asks, how do the graphs indicate that the reaction is second order in NO2? Okay, so really interpreting these graphs, an essential skill for AP Chemistry students. If we look at the very first graph that we were given, right, that plotted the concentration of NO2 versus time, all right? This is not a linear graph, all right, which means it must not be zero order in NO2 because otherwise this plot would be linear. If we look at the bottom left graph, that plots 1 over the concentration of NO2 versus time, and this does give us linear data. And so that tells us that it's second order in NO2. Just to confirm, let's look at the final graph. That plotted the natural log of the concentration versus time, and that is also not a linear graph, and therefore it is not first order in NO2. So our answer to part A is the plot of 1 over NO2 versus time is linear. That's how we know the reaction is second order and not zero order or first order in NO2. And that's what you had to write down for 1 point. You did not have to write down the reasoning behind your answer, but you do need to know how to work through this. Okay, let's go on to part B. Write the rate law for the decomposition of NO2. Now, we were told it's second order in NO2. So what that means is that when we write our rate law, we have to have NO2 raised to the second power. Rate equals K times NO2 squared. K is the rate constant, it should be written as a lowercase k, square brackets for the molar concentration of NO2, and then the exponent of 2. That's what you needed to write down for 1 point. All right, let's go on to part C. Consider 2 possible mechanisms for the decomposition reaction. All right, so here's mechanism 1, and the question asks, is this rate law described by mechanism 1 consistent with the rate law that we wrote in part B? All right, so in part B, we said it was second order, and let's look at mechanism 1 and see if they go together or not. So really the key is to look at the slow step of the mechanism, all right? The reactants of the slow step of the mechanism, which is step 1, are really what define the rate law for this mechanism, all right? The slow step, or the rate limiting step, is step 1. So it's got 2 particles of NO2 colliding. It's bimolecular in NO2. And the way these elementary steps work is that the rate law for an elementary step literally comes from the reactants. And so the rate law would be second order in NO2. All right, and that exactly matches the rate law that we wrote in part B. The experimental rate law from part B and the molecularity of the slow step in the proposed mechanism match. And that's really what we need to write down. So yes, it is consistent. You need to have an explanation and say that yes, it's consistent to get the point. All right, and then let's go on to C part 2. we have a second mechanism that's proposed here. Is this rate law consistent with the rate law that we wrote in Part B, where we said it was second order because we were told it was second order in NO2? All right, now this mechanism is a little more complicated. All right, if we look at it, step 1 is a fast equilibrium. Step 2 is the slow step, and that's our rate limiting step. So if we write the rate law for step 2, remember that comes from the reactants of the elementary step. The rate for step 2 would be the rate times the rate constant for step 2 times the concentration of N2O4. But N2O4 is an intermediate in this mechanism, right? It's produced in step 1. It's a reactant in step 2. We don't normally write rate laws in terms of intermediates. So we need to do a little more work here. And the key to doing this correctly is to recognize that step 1 is a fast equilibrium. And that means the rate of the forward step of step 1 equals the rate of the reverse step of step 1. And so we can write rate laws for those processes, for the forward and reverse processes, and set them equal to each other. All right. So the rate law for the forward step would be K1 times NO2 squared equals K minus 1 times N2O4. So I call K1 the rate constant for the forward step of step 1 and K minus 1 for the reverse step of step 1. And then based on what's colliding in those steps. And I set them equal to each other. When I do that, I can now rearrange this equality to isolate N2O4. All right, so I can rearrange it and do that. And then I can substitute this into my rate law for step 2, okay? And when I do that, I end up getting rate equals the rate constant, if I consolidate all my rate constants, times NO2 squared. Does that match the rate law that we wrote in Part B? Yes, it does. And it is consistent, and that's our answer, what we need to say for 1 point. You definitely need to be able to do these problems where the first step of the mechanism is a fast equilibrium and solve for that intermediate and substitute into the rate law for the slow step. It shows up fairly frequently in AP Chem. It's more involved, but definitely doable. How did you do? The average score on this question in 2019 was 1.32 out of 4 points. So most students answered 1 or 2 of the parts of the question. Some answered 3. It was hard to get all 4 points. Very doable, but if you know your chemistry well, you might have gotten 3 points. You're doing very well if you got 3 or 4 points on this question. And there's a lot to do. So subscribe to my channel. I'll keep posting more videos.